So, for some reason, my lecture is written on pages that are in a random order. I think I've been in Berkeley too long. I need to get out. So hopefully I'll survive till tomorrow. Oh, photo. Apparently there's a photo, and apparently it's today. And apparently it's in an hour and a quarter. So there you go. Hope you've all bought a nice change of clothes. Or whatever. So photo 1045. I was told last night. Sorry. I don't know where it is, but at 10:45, if you just wander off, then you won't be in the photo. I think that's it as far as admin goes. Right, so now I need to tell you, so last time, I stated this kind of web of, this kind of web of modularity, right? Was stated. So I talked about this. I had some 3x2 thing, and several of the objects weren't even defined. But in the middle, there was some kind of there was something that actually made sense, right? There was algebraic automorphic representations for some G over K. So G, G is whatever. G is GLN if you like. But I mean, just let me tell you the kind of the full truth. If G is any, or G, any connected reductive group, right? So really, I'm going to, somehow. For GL2 and GLN, it's kind of nice because there's kind of concrete examples of stuff. But when you're actually defining these abstract things, you don't need G to be GLN. You can just let G be any kind of symplectic or orthogonal group or all sorts of things, right? So algebraic automorphic representations for G over K should somehow correspond to compatible systems of L-adic Galois representations. Well, semi-simple, let's say. L-adic Galois representations. Whatever, gal K bar over K into some kind of L group, right? So there's just some fancy, there's some fancy way of writing it, and maybe these should somehow correspond to motives, right? Well, I don't know. Let's not go with motives. I think for a general G, I'm not really sure what a G motive is for general G. So if G is GLN, and then kind of LG is also GLN. Let me just. I don't really want to get bogged down in the details for general groups because I'm trying to make this as comprehensible as possible. But what I'm saying is there's a general machinery that you can feed in any of a large class of algebraic groups and get some kind of crazy conjecture. So there's all. I mean, for a general G there are subtleties, right? There's all sorts of subtleties. I've never written on this book before. I'm not going to start now. For general G, there are subtleties. And I really want to kind of not worry about these. So this is why this is 10 minutes on general G. Forgive me, right? The reason I wrote this paper with Toby G was precisely because although the experts all knew this, when you tried to when you actually tried to pin people down, they were very vague about what does algebraic mean, right? So for general G, there are subtleties. Let me just tell you what they are, and then we'll move on from general G and we'll go back to GLN. Okay, so here's the general story. And of course, I still owe you a definition. That's the main thing we're going to do today. For general G, there are subtleties. And the subtleties are just the following kind of rather tedious list. So there's more than one notion of algebraicity. And I can explain this to you easily, right? It's just to do with those fudge factors. Okay, we had this blasted norm A over D to the power half, right? So this phenomenon is an issue even for GL2. And the issue is norm A over D to the power half sometimes involves the square root of P, right? And if you're not careful, you take something which is supposed to be algebraic, and then you try and figure out what E0 is, and you leave these normalizing factors somewhere where you shouldn't, or you don't put them somewhere where you should, and all of a sudden you discover that your coefficient field, which is supposed to be a number field, E0, contains the square root of infinitely many prime numbers. And that's not good. And the reason that's happened is not because the conjectures are all broken, it's because you haven't quite got algebraicity right. Okay, so me and Toby G christened these C algebraic and L algebraic. So I will say something about these notions for GL2 later. Okay, so you have to kind of figure out exactly what you mean by algebraic, right? It's well understood, but there are subtleties. So the next subtlety is that this thing here isn't a bijection. Okay, so what I'm trying to do is I'm trying to tell you the full global Langlands conjectures in some form where both sides actually make some kind of sense, because I don't really want to talk about representations of the global Langlands group. We'll come back to the global Langlands group later. I've been kind of dismissing it all the time during these talks, but there is a reason. We'll see the reason for the global Langlands group later as well. So there's more than one notion of algebraicity, so you have to kind of figure out exactly which of the algebraic things are supposed to be matching up. And then this thing here, this thing here that looks like a bijection is not a bijection for general G. Okay, and again, it turns out that's for several reasons. For several reasons. Okay, so I'm just going to tell you some words, right? On the left-hand side, we have some issue of local and global L packets, whatever they are, okay? Okay, and this issue doesn't exist for GLN, right? But this is just some words that you hear. As you go through life, you hear people talking about L packets and even now A packets. And all that's happening there is you have automorphic representations which kind of at two places, then, they're not isomorphic, but they're somehow in the same packet, and so maybe they should give you the same Gauss representation. So the idea about an L packet, pi's in an L packet, give me the same row. Okay, so there's these weird finite, this is a local L packets are finite. So this is some kind of finite to one correspondence this way. Or maybe if your local L packets are finite, but your global L packets are products of local L packets, you could imagine global L packets being infinite. So maybe there's some issue going this way. And going this way as well, there is some issue with Langlands parameters, different global Langlands parameters. Different global Langlands parameters. We're leaving this nonsense quite soon, so just bear with me for 10 minutes. Different global Langlands parameters on the right-hand side. On the right-hand side. Might be equal everywhere locally. Maybe isomorphic everywhere locally. So there's just some, maybe this will make more sense once I really start, I'll get back to GLN and I'll really start kind of taking apart what I mean by this. So the upshot is, for a general G, this is not a bijection, right? This is some kind of, this is some sort of correspondence, right? And, you know, you have to make sense of it. And what me and Toby G did was we said, you know, we attempted to formulate this conjecture rigorously. I mean, whether we got it right or not, time will tell, right? But the way, you know, one way of thinking about it is that an automorphic representation, pi for G, which is algebraic, should go to rho pi, should go to some Galois representation, kind of defined up to some kind of Tate-Shafarevich group. So I think that's probably all I want to say about it. So there's all sorts of subtle issues, right? So the upshot is there are subtle issues here that I don't really want to get bogged down in. Subtle issues. There are subtle issues for general G. So these Tate-Shafarevich groups are all trivial for GLN, right? These are all equals 1 for GLN by Brouwer-Nesbitt. So that if you have two semi-simple global representations which are isomorphic everywhere locally, then they're globally isomorphic. So in general, there are sort of global objects which locally look the same but globally don't look the same, and that sort of thing is called a Tate-Shafarevich group, or a class group, right? So there's subtle issues for general G. So I want to, you know, this course is really, although I know something about general G, I wrote a paper on it. And the reason I wrote the paper on it was to try and understand what was going on, in fact. But let's forget general G. Okay. So for general G, it's not quite a bijection, it's a correspondence. Yeah, I don't quite understand how you can start going on about motives unless you understand motives with motivic group LG or something. So let's forget it. So conclusion, let's forget general G when talking about Langlands correspondences. Because we don't really, when talking about Langlands. Because I want to do something I understand. So let's stick to GLN. Right. So then this thing becomes, I said it was a conjecture of Clausel last time, and some people might argue that probably this was all implicit in Langlands, right? So for GLN you can choose, right? You can choose. Right? There's a very clear paper by Laurent Clausel where he lays everything out, or there's Langlands Corvallis. Langlands Corvallis. You can see in Langlands he's already dreaming of motives, right? Right, and then Clausel 1990. Sort of concrete conjecture. Plus an amazing theorem, right? A statement of an actual theorem, right? And what Clausel actually proved in 1990, Clausel proved there, if you've got some automorphic representation of GLN over K, and then there's a catch, right? such that, firstly, K has to be totally real or CM. And secondly, some very strong duality condition on pi. Strong self-duality condition. On pi, which is not going to be satisfied by a random pi, but the methods of the paper, you were kind of stuck with this. So this is both of these are very strong conditions, because what percentage of number fields are totally real or CM? 0, and what percentage of automorphic representations have got this duality condition? Actually, nobody really knows. I've heard some people suggest that a generic representation might be dual in this way. So this is some condition of mysterious strength, but when you think about it, people like to give the impression that we're really, really kind of racing away, solving lots of Langlands conjectures, but there's this huge restriction. So Clausel, then 3, he has to assume that pi is algebraic, but he needs more than algebraic, kind of a strong algebraicity condition. Right? It was called, I'll call it cohomological. There. Given those things there, Clausel constructed the compatible system. So how did he do it? Well, there's only one method, and so we use that method, right? The only way that we know 2 ways of constructing compatible systems of analytic Gauss representations. And back in 1990, arguably, we only knew one way. And the one way we knew was et al. Cohomology of algebraic varieties. So what Clausel did was he used et al. Cohomology of algebraic varieties. So which algebraic varieties did he use? Well, he used the only ones whose cohomology we know to control quite well, which are Shimura varieties, right? So Clausel's proof looks kind of easy, right? Clausel's proof. You just, firstly, step one, find an appropriate Shimura variety, right? Find appropriate Shimura variety. This is just, some algebraic variety defined by some polynomial equations. Step 2, relate the cohomology of this variety to automorphic forms. And then step 3, done, right? That's how the proof works. It's kind of very simple, really. So there are standard machines which do a lot of this stuff. And what the standard machines do is they translate the question, the standard machines translate the question down into something very specific. Basically, what happens is we have these random algebraic varieties parameterizing abelian varieties with some extra structure or whatever. We compute the cohomology of these varieties using a machine, and the cohomology spits out some relationship. The machine spits out a relationship between the cohomology and various automorphic forms, and then the automorphic forms we have Frobenius acting on the cohomology, and this is somehow related to some Hecker action. And there's something that needs to be understood here. And this goes under the name of Eichler-Shimura. There's some Eichler-Shimura relation telling us that Frobenius is related to Hecker, and that tells us that, I don't know. That's what Clausel's proof looks like. And now fast forward And fast forward to 2013. And we get Harris, Land, Taylor, Thorne. And they remove the duality condition. They remove the self-duality condition. So they prove, again, under this huge restriction on K, they remove the self-duality condition, but they still have the algebraicity condition. They remove this. And then Schulze gives a second proof using this fancy perfectoid stuff. So how did they remove that self-duality? Again, the idea is really easy, right? So here's the idea. Given pi, then we somehow just do pi add its dual, right, is now self-dual. And that's self-dual, but by add, I mean some slightly complicated thing. This is a representation of GLN, and this is a representation of GLN, and this is a representation of GL2N of some adelic group. So this addition is some slightly subtle thing. So that's self-dual. So use the cohomology of Shimura varieties, and the cohomology of Shimura varieties doesn't quite work, but the cohomology of Shimura varieties gives you somehow representations which are close to the representation you want. So then it turns out you have to take limits, right? At the end. Take limits of cohomology of Shimura varieties to get the row you want. So that's a summary of everything we know about GLN, as far as I know. And then there are results going the other way. And results going the other way, I guess the most recent one is this 10-author paper. Maybe I won't talk about that now. So there's some kind of idea about how we get from automorphic representations to Gauss representations. And I should maybe say, so what were the, somehow the genesis of these ideas, or I guess Weil's theorem that I sketched last time, Weil's construction of some chi, some Grierson character, gives me some representations rho chi, one-dimensional analytic representations. So there was Weil's original construction that I whizzed through yesterday, and then the next thing that happened was Deligne, I guess. I mean, Eichler and Shimura. And Deligne. And Deligne-Serre. So that's the kind of the full attribution of the thing I'm about to tell you. So this is for k is 2, and this is for k bigger than 2, and this is for k is 1. So what do these people prove? If f is a weight k modular eigenform, so just a modular form, a weight k, you've got a modular form, an eigenvalue for the Hecker operators, then there exists a compatible system of Gauss representations. A compatible system of two-dimensional Gauss representations of Gal Q bar over Q. And Deligne's proof says, you see, this was maybe the early 70s, and et al. Cohomology had just been invented. So Eichler and Shimura had done the weight 2 case by looking at tape modules of abelian varieties. And then it turned out that tape modules of abelian varieties were actually et al. Cohomology, because étale cohomology has been invented now. So Deligne was like, why don't we use some fancier varieties and take the étale cohomology of them instead, and then he can do all k at least, all k2 or more. And then k is 1 is a funny weird. Do you remember there are two kinds of compatible systems of L-adic Galois representations. There's genuinely non-trivial ones, like the cyclotomic character, and then there are these bogus ones, where you just have like a finite order Dirichlet character, and it takes values in GL1 of some finite extension of Q, and you just embed that finite extension of Q into the L-adic numbers for all L and say there's a compatible system. So there are these bogus ones which have really got finite image and are a system of L-adic representations, all of which are the same in some sense. So that's what happens. That's what happens in weight 1. In weight 1, the image is finite, and the fact that there's a compatible system is kind of a misleading assertion. In weight 1, you get rho from gal q bar over q, basically to GL2 of q bar with finite image. So that's a slightly different situation to weights 2 or more, and somehow it needed a separate argument. So what do we conclude? So as I say, Deligne introduced in some sense the key ideas, because he said, we're going to prove this using cohomology of Shimura varieties. Right? And that's exactly what he did. He used étale cohomology of modular curves. And what we can conclude from this is that it looks like a modular form should be an automorphic representation for GL2 over Q, right? When you look at, so if all this is supposed to be some kind of coherent picture, then, so for Deligne's theorem to fit in, into this coherent picture, and I suppose another person, it should be stressed, the importance of these people kind of falls by the wayside in some sense. But it was Serre that spotted that this might be true. It was Serre just staring at the delta function going, do you know what? It looks like there's a compatible sequence of Galois representations attached to that delta function. That's what happened, right? That's where there you see a genius, right? Q minus 24Q squared plus ... right? Ramanujan looked at that and was like, oh, no way, like, A2 times A, what's this? This is sum of tau of NQ to the n, right? Ramanujan looked at that and was like, whoa, no way, kind of tau of 2 times tau of 3 is tau of 6. Like, what the hell? That's like, no holomorphic function should have that property. So Ramanujan looked at that and was like, no way. And then, lo and behold, that gets proved. So it's the same sort of story, right? Ramanujan proved that kind of tau of p was congruent to 1 plus p to the power 11 modulo 691. Whereas 691 is just some random large prime. This isn't a special case of a general phenomenon. This is just some weird thing, right? This is q times the product of 1 minus q to the n to the power 24. This is not a mysterious... the definition of this power series expansion is not mysterious. So there's this power series expansion, and occasionally geniuses look at this power series expansion and make observations that kind of really push the theory forward. And Ramanujan noticed that the coefficients seem to be multiplicative, proved by Mordell, I guess, maybe, or Hecker, I don't know. And then Ramanujan also noticed this crazy thing, and Serre said, maybe there's a 691 adic Galois representation attached to that. Obviously, that's the first thing you say, right, when you see this congruence. Maybe there's a 691 adic Galois representation attached to delta, and maybe it's two-dimensional, and maybe modulo 691, it's going to be is the trivial representation plus the cyclotomic character to the power 11. Right? That would explain this, wouldn't it? So that's what Serre said. So then Serre goes and tells Deligne to construct a 691 adic Galois representation attached to the delta function, and Deligne goes and does it. Right? Took him a year or two. So that's what happens when intelligent people look at kind of seemingly trivial things. So it was Serre that said that this construction should exist, and it was Deligne, who, real master of the arts of étale cohomology, managed to prove it, and now we see it as a special case of a general phenomenon, except you don't see it as a special case of a general phenomenon, because I still haven't told you what an automorphic representation is, and I still haven't told you how we're going to get one from a modular form. So maybe it's time to do that. I've been putting this off, you can probably tell. I was thinking of kind of leaving it to the very last. I was playing with the idea of continually telling you I was going to say what it was and then kind of never getting around to it. But I don't know. I'm slightly worried I'd be lynched if I didn't tell you now. So I think I'm going to tell you what an automorphic representation is. Oh, no, I'm not. I'm going to tell you what an automorphic representation isn't. That's right. So here we go. Right, that's the next thing. So what isn't an automorphic representation? That's the next thing. There. So here's the idea here. So recall the local Langlands conjectures, okay? There's a stupid subtlety here, and it was something. It is again. This is me. I'm going to go on for like 15 minutes about something that one day dawned on me when I was some postdoc, and again, it's one of these things. For some reason, it took so long to dawn on me because no one ever explicitly wrote it down. So let me explicitly write it down. I mean, maybe someone did explicitly write it down and I missed it. So the local Langlands conjectures. What are these? So now I have K of a QP finite. Okay, and what do? I take all smooth, admissible, irreducible representations of GLN of a K. Okay, of GLN of K, right? I take them all. I set up some theory of representations of this group. If you ever engage with any question about I of chi1, chi2, here's a conjecture. Here's a meta conjecture. For those of you in the there are people in the room for whom that looks like some scary, weird thing, and there are some people in the room who think, "Oh, yeah, I've seen examples of that. That's not scary and weird at all." And the people in the room who are not scared of it are exactly the people that attempted to do any exercise at all about I chi1, chi2. That's why I said you should do it. You do I chi1, chi2, you get the hang of one example of one of these. So. We do all smooth, irreducible, admissible representations of GLN of a K, and they're supposed to match up with some n-dimensional Vadeline representations. Okay, but the point is, you do all of them here, right? And I guess these are F semi-symbol or something. Okay, so that's what the local Langlands conjectures look like. We have a group. And then we have we have a Galois-like group and a representation theory-like group, and we're saying we understand all the representations of that group via this strange correspondence. So the global Langlands conjectures can't look like that, right? Global Langlands conjectures they're about automorphic representations, okay? They're going to be about automorphic representations of GLN of the Adels of K, right? That's what they're going to be about. We're going to talk about representations of this gigantic group, but they are irreducible, it turns out, right? So an automorphic representation is by definition an irreducible representation of GLN of the Adels of K. Now we know about the Adels of K. They're this weird there's this restricted product, right? Adels of K is the restricted product over all places V of KV. Okay, and that product is hiding information. This product is saying for all finite places V, for all but finitely many of these finite places, this thing should be integral or whatever. This is hiding information, and now is a good time to hide that information because I'm thinking slightly vaguely, right? So the Adels of K is some huge product of these groups here. And so therefore GLN of the Adels of K is some huge product, right? Some restricted, I'll just put that dash there, and the definition of the dash is it makes it work, right? GLN of KV. Right? That's somehow what GLN of K must be. And in fact, that's exactly what GLN of K is, in fact. GLN of K is matrices in GLN of KV for all V, such that for all but finitely many V, you're in GLN of OK. I mean, that's absolutely how it works. GLN of OK. V. So we're in GLN of KV, you know, for each V we have an element of GLN of KV, and for all but finitely many V we're in GLN of OKV. That's what GLN of K is, but don't think about it like that. Just think about it as a product of a load of groups. Okay? And now there's a general theorem in representation theory that says if you've got a representation of a product of groups, then that representation is just a tensor product of representations of each of the group, right? If I've got, you know, G and H are finite, if I've got two finite groups, and I've got rho, some representation, irreducible, well, V, some irreducible representation of G cross H, here's a fact, right? V is kind of V1 tensor V2, where V1 is an irreducible representation of V, sorry, irreducible representation of G, and V2 is an irreducible representation of H, right? There's some fact that maybe some of you learnt when you were doing undergraduate representation theory. I think it was just about in our undergraduate representation theory, because the tensor products are a little bit scary when you're an undergraduate. But that's how it works. You get an irreducible representation of the product. It turns out to be a tensor product of irreducible representations of the factors. Now, I guess these groups aren't really finite, and this isn't even really a product, but, you know, if you're prepared to gamble, then maybe you'll be prepared to accept that if I have an irreducible representation of GLN, so maybe if pi is some sort of well-behaved, is a nice, well-behaved, irreducible representation of GLN of the Adels, maybe pi is then, maybe pi, you see, it's going to be an infinite tensor product. I'm just going to put a primed, because like that's what you do. You put a primed and you don't bother explaining it. Maybe it's some weird primed tensor product of pi v, where pi v is an irreducible, admissible representation of GLN of KV, right? And it turns out such a statement is true, right? This is indeed true. So you can read about this Flath's article in Corvallis. You can see all the gory details. But at the end of the day, it's a mild generalization of something that you already know. Okay, so I've got my automorphic representation of GLN of the Adels. I know I haven't defined that, but you know, this is going to be a representation of this global thing, and it's going to split up as representations of this local thing, right? So there's our automorphic representation. Pi, it's our local components. And now here's the idea. These pi v's, you see, these pi v's, here's the idea. If my automorphic representation pi is supposed to correspond to a compatible system of Galois representations rho, compatible system of L-adic Galois representations, then pi, because this is going to be an irreducible representation of GL2 of the Adels, pi is going to factor as this tensor product of pi v's, where these pi v's are things we've seen before, right? These are representations of GL2 of a local field. And the idea is that pi v, if v is a finite place, I'll just put p, right? If p is a finite place, this, by the local, so this is global Langlands. By local Langlands, this maybe pi p should correspond to, I need a local Wedelin representation, right? That's what I need. And I showed you how to do that, right? There's this proposition of Grothendieck. You simply look at rho from, I look at the restriction of rho to gal kp over kp, right? And that's now an L-adic representation to gln of ql bar. And then this proposition of Grothendieck shows how, to given one of those, you get some L-adic representation, Wedelin representation. Let's just call it WD of rho. So I've got this lovely compatible system, and I can look at what's going on at some finite prime. I get a local Wedelin representation. And so this should be what's happening, right? This is my local Langlands, the local Langlands correspondence. So I've got my global rho that's matching up with some global pi whose definition we're missing. And I can look at my global rho locally, and I get local gamma representations, which by some machine which we talked about earlier gives me local Wedelin representations. And my local Wedelin representations, maybe I'll put a little p there. My local Wedelin representations should match up with my local smooth admissible irreducible representations coming from pi. Right?
Okay.
Hey.
So are those two different p's?
Right, yeah, let me get my p's straight. This is a p, and that pi p is going to be a representation of gln of kp. And that p is finite. So that was what we talked about last week. And so now I've got this is a global rho. So these representations are gal k bar over k. K is global to gln of ql bar. And my global rho, I can restrict it to a local, so I think this is kp bar over kp. The same p, but a random L, right? The L is random, L not p. And by Grothendieck, given an L-adic representation of this, I get a Wedelin representation of this, yeah. I get a Wedelin representation. And that's the thing that's supposed to correspond. So that's how the global Langlands correspondence is supposed to mix with the local Langlands correspondence. And the reason I mention this is because this has a really concrete consequence, which is that an automorphic representation of gln of the adels of k is not, so here's a consequence. The definition of an automorphic representation of gln over k cannot be it can't be an arbitrary, smooth, admissible, irreducible representation of gln of the adels of k, right? So locally, that was exactly the story. Locally, we came up with a group, gln of k. K is now, just for this board only, k is a finite extension of qp. We had a local field, and we looked at all representations of that local field, and they matched up with all n-dimensional representations of some Galois group. Okay? So if globally, our global Langlands correspondence, our automorphic representation is just supposed to be some random, smooth, irreducible, admissible representation of gln of k, that can't be the right answer, because we can just build, right, random, smooth, admissible representations of gln of k in some we can just do random things. So here's an example. Why not? I mean, here's an example. Let's do GL1, right? I'm going to attempt to build an automorphic representation of GL1 over k, but because I'm going to these lectures, I don't know what an automorphic representation is yet, because the lecturer still hasn't told me. So I'm going to have to guess. So I'm going to guess that an automorphic representation of GL1 over k is just a representation of the Adel group. I'm going to guess incorrectly that an automorphic representation of GL1 over K is just a representation of AK star, which is some tensor product of KV star. Some weird restricted product. So I need to get a representation of AK star. So I need to write down a representation of KV star for all places V, and then I'll get a representation of AK star. So that's great. I think this sounds like a fabulous prospect. I'm going to write down a representation of AK star. And how am I going to do that? Well, AK star is this product of KV stars. So to write down a representation of AK star, okay, because I haven't quite understood this consequence yet, to write down a random representation of AK star, I just need to write down random representations of KV star. Let's do K as Q, right? I need a representation of Q2 star. Okay, well that shouldn't be too difficult. I'll just send Z2 star can go to the identity. Right, I'm going to write down a one-dimensional complex representation of the adels of K, right? Right now, I'm going to write down a one-dimensional representation of the adels of K. So I have to first of all define, I'm going to do it piece by piece, right? I need a representation of QP star for all primes P and a representation of R star. So I need a representation of Q2 star, well, the hard part is Z2 star, that can go to 1, and 2 can go to, I don't know, I just need some complex number, right? I don't know, 7. Okay, because it's my favorite number. So now we need a representation of Q3 star. Well, I don't know, unramified representations are the best, so I'll send Z3 to 1, and 3 generate. You see, because Q3 star abstractly as a group is generated by Z3 star and the uniformizer, which is 3, and I'll send it to 7, because 7 is my favourite number. So I'll do that to QP star for all P less than 100. There, I'll send ZP star to 1, and I'll send P to 7. Okay, and then I get a bit tired, and I want to go have a break, and so I pass it on to my PhD student, and I say, can you please continue defining this automorphic representation? And my PhD student can't be bothered, so for P greater than or equal to 100, my PhD student just says, I don't know, let's just send all of QP star. I mean, 7 is a stupid number. Let's just send all QP star to 1. Oh, and then we've got to do R star as well. Let's just send that to 1. Okay, great, we're done. Okay, so I come back, and he says, finished. It's like fabulous. And indeed, lo and behold, we've got a representation. So you see, that representation of Q2 star, we could call it pi 2, right? So it's the complex numbers, and this group is acting on it. Remember, this group is abstractly Z2 star cross a group generated by the number 2, right? So Z2 star is acting trivially. This free rank 1 abelian group, all I have to do is say how a generator acts. 2 will act by 7, 3 will act by 7. For all primes less than 100, P will act by 7. And then for all primes P 100 or more, P is just going to act trivially, because that was what my graduate student decided. Okay, so there we go. So now we have pi P for all P, and we've got pi infinity. We need a representation of GL1 of the R. It's the trivial one-dimensional representation. Great. And we define pi to be the tensor product of pi V, right? And here's a random representation of GL1 of the adels of Q. And I'll note that it's easy to write down representations of GLN of the adels of Q in just the same way, right? I told you about I chi1 chi2. That's a representation of GL2 of QP. So we can just choose random chi1 chi2s for all primes P, and then we get representations of GL2 QP for all primes P. We tensor it together. We could put the trivial one-dimensional representation of GL2 of the reals in, and Bob's your uncle, right? It's really easy to write down representations of GLN of the adels of Q, because all you do is you take local representations, you tensor them together, and you put a little dash there to indicate that there's something going on behind the scenes that you're not too bothered about. So representations of GLN of the adels of Q are very easy to come by. And as you can probably see from this construction, there's a lot of flexibility, right? I mean, there's nothing special about the number 7. That was just sort of a joke number. So let's say that's an automorphic representation. If we believe in the global Langlands philosophy, that should give us a Galois representation, right? So let's say pi is an automorphic representation. Of GL1. Then there's going to be an associated compatible system of Galois representations, right? Then by the global Langlands philosophy for GL1, pi gives me rho, like let's just say rho L, gal q bar over q, there, to GL1 of QL, right? And now what's this going to be? I guess rho L, what do we know? We know that rho, by this local, you see, if I really want, if this correspondence, pi to rho, right, if it respects the local Langlands correspondence, which we understand quite well for GL1, and the global correspondence should respect the local correspondence. If the global correspondence respects the local correspondence, then because my graduate student annihilated every prime p bigger than 100, then that means rho L of frob p is the identity for all p bigger than or equal to 100. Right? But these are dense in this Galois group, so that implies that rho L is the identity, trivial one-dimensional representation. Right, by Chebotarev. But this is really bad, right? And that implies that kind of rho L of frob 2 is 1. But I wanted it to be 7. That was the whole point. I was making them all 7. And then the graduate students come along and decided that these infinitely many things should be 1, and I don't get to be it doesn't get to be 7. Right? So I can't just be going around defining rho p's randomly, okay? So the upshot is that the definition of an automorphic representation of GLN of the Adels of K cannot be take any old irreducible representation. You know, plus some continuity conditions, whatever, smooth admissible. Whatever, you know, maybe these words make sense, I don't know. Yeah, they will make sense. You see, this is in stark contrast to the global case. There, that's the first main thing I wanted to explain to you today. The definition cannot be, let's just take some random irreducible representation of this adelic-like group. Okay? We have to, so where are we going to find them, right? Where are we going to find them? Huh? Yeah. No, I'm just kind of talking vaguely. I mean, I didn't really tell you what this infinite tensor product was, right? You have to assume you're unramified at all but finally many places, and then you take some direct limit. And it will be admissible because you're unramified at all but finally many places. You know, I haven't done this properly yet because I don't really need it. This is just... This is just me trying to motivate what's going on. So let's go back to GL1. Why didn't this work, right? I did this was totally fine, right? This is definitely a construction of an irreducible representation of GL1 of the Adels of Q, right? So why is our pi no good? Why is our pi no good in this GL1 case? What I've done is I guess I'm defining a map. This representation, this pi, is a map from AQ star to C star, right? That's how I can think of it. That's what a one-dimensional representation is. Okay? And if you think about it, what were we doing yesterday and the day before? That's not what we were looking at, right? We were looking at something else. We were looking at pi from AQ star over Q star to C star. There's some subtlety that we've missed. We built a random one-dimensional representation of the Adels, but there's something wrong with that representation. There's this thing here. There's this Q star, right? So Q star embeds diagonally into AQ star, right? So what about our crazy pi with the 7s in? Is it trivial on Q star? And it better not be, because if I have a representation of this group, I showed you last time I really do get a compatible system of Gauss representations, at least it's algebraic. This one had better be algebraic because it's completely trivial at infinity. So it's as algebraic as they get. Our crazy pi, is it trivial on Q star? Let's try and work out what pi of 2 is, right? So that means pi of 2 embedded diagonally, right? 2, 2, 2, 2, ... 2. Right? That's what an Adel is, right? That's 2 considered as a 2-adic number, 2 considered as a 3-adic number, 2 considered as a 5-adic number, and at the very end, 2 considered as a real number. So what's pi of this number 2? Oh boy, it's not 1, right? Because for p equals 2, so this 2 here, Z2 star gets sent to 1, but 2 gets sent to 7. So this 2 here goes to my favourite number. So this equals 7 from this guy here times, and now this guy here, where does that 2 in Q3 go? I decided to kill all the 3-edit units because unramified things are nice. So 2 is in Z3 star, so it goes to 1. And I killed all the units for p less than 100, and then my PhD student killed them all for p bigger than 100 because they killed everything. And at infinity, we've got a number 2, and that got killed as well. So that equals 7, which isn't 1. So what I'm trying to really hammer home to you is that there are local Langlands conjectures which match up all representations of GLN of QP with some Gauss representations, but globally there's some subtlety. We can't just take random local things and glue them together and say, this is a global automorphic representation, because you can't do that, right? There's this sort of weird piece of extra magic, okay? And you see this in the literature. When people are struggling to understand this concept of where this extra magic is, you see it throughout the literature. You see primitive definitions. I mean, you still even see it in some of the modern literature. But people don't want to when people try to explain things like CM elliptic curves, but they're reluctant to introduce the Adels, and yet they say it turns out that given a complex elliptic curve with complex multiplication, there's some kind of canonical Grierson character attached to that. And people that want to explain what that is, but they don't want to delve too much into the Adels, they have to think of some way of talking about Grierson characters without mentioning these Adels. Right? And I kind of showed you that if you had AK star, there was the finite part of that, there was a map from this to the fractional ideals. And so people sometimes, instead of introducing this stuff, they start looking at maps. So you see this in the literature. You see in the literature, sometimes it's called a Hecker character. See in the literature the notion of a Hecker character. It would not surprise me, I'm not really a historian, but Hecker's work was from the 1930s, and I think that was when Hensel was defining the p-adic numbers around that time. So it would not surprise me if there weren't any Adels. There couldn't have been Adels in Hecker's work. Because even though there might have been local fields, there was no Idels and Adels. So you see Hecker characters, which are characters of ideals. You see chi from kind of ideals prime to n, there, to the complex numbers. But you don't just take a random chi, ideal prime to n. You always demand that such that if alpha is congruent to 1 mod n, then kind of chi of alpha is some sort of sensible thing, is some like, I don't know, alpha to the n or something. right? So I won't plough through the kind of historically relevant definitions. You can read, like Tate's article in Cassels-Fröhlich talks about classical definitions of Größen. The definition of a Größen character changed at some point, right? You could think of it in the rather abstract way. Well, no, you think of it in this sort of funny way that doesn't involve the Adels at all, as just functions on ideals that were somehow multiplicative in some way and satisfied some property, you see. And what's happening here is that this random function on ideals prime to n is one of these, and then this condition here, that if you're somehow equal to 1 mod n, then you're behaving in some certain way. You see, the idea is you fix that then. These ideals prime to n are all about the finite part, and then at the infinite part you somehow fix up this problem by putting an alpha to the minus mn, you see. So you put alpha to the minus m at infinity, and then you get some map from ak star, but it's got k star in the kernel to c star. So there's this k star that somehow is sometimes difficult to see it, but when you see things like this, that was the original kind of rather primitive ways of saying that something has to be trivial on k star. So there's some subtlety, right? An automorphic representation of GL1 of AQ is not just a representation of this. It's a representation of this that has some magic extra property. And the magic extra property in this case is that Q star is in the kernel, right? And as I've tried to convince you with this kind of stupid trying to build a Größen character by saying what's going on at every prime, what I've tried to convince you is that if you do that randomly, then it's not a very good way to build them, because you end up with your Q star behaving kind of rather randomly, you see. So there has to be some kind of coherence between the local components. So if G is a finite group, and I want to understand all the representations of G, I want all the representations of G. Where am I going to find them? Find them in the group ring, right? Irreducible representations of G over the complexes. I can find them in the group ring. C of G. Because that by, the somehow a summary of the entire undergraduate typical representation theory course is that this group ring here turns out to be isomorphic to a direct sum over pi, an irreducible representation of G. You do pi to the power of dimension of pi. There's just some weird formula. Okay? And in particular, if I'm interested in irreducible representation, it's got dimension at least 1. And so it shows up on the right-hand side with multiplicity at least 1. So it shows up on the left-hand side as well. Okay? So if I've got a random finite group, and I wanted to look at all the representations of that group, then I could look at the group ring. Okay? Now what about... if I'm not interested in all the representations of this group, I've just spent 3/4 of an hour trying to convince you that we are definitely not interested in all the representations of GLN of the Adels. Because it's really easy to build a representation of GLN of the Adels. Take random representations of GLN QP, just tensor them together. Okay? That will give you a random representation of GLN of the Adels, which is nothing more than just choosing. It's like saying write down a random power series expansion and hoping that it's a modular form. Right? That's the analogous assertion. Right? So for groups, we kind of know where to find all representations. We can just look at that. Okay. Now here's a sort of a funny thing. If H living in G is a subgroup, what we could do, we can look instead at C of H mod G. I'm not saying H is normal, so this isn't a quotient group, but this, this is literally functions from the set H mod G to the complexes. So H mod G is by definition the set of cosets, right? HG for G and G. So H is a random subgroup. We look at this quotient set. We could look at all the functions from H mod G to C you see, and we could define G star phi of gamma to be phi of gamma G, right? And now you have to do some exercise to check that this is well defined. And an action, how do you prove it's an action? Write maps on the right, right? Let's write maps on the right just for 1 second. G star phi, I need to prove this is gamma G. I'm writing that as the definition, and you see all the things are in the right order. So how do you check it's an action? It's obvious, right? So this is well defined, this is an action. And it's a subspace, right? And it's a subspace of C of G. Because C of G is just functions on G, and this can be regarded as functions of G which are constant on cosets of H. So there's a funny thing, right? So I've got my group G, I've just written that, and I write down a random subgroup H, and then I can look instead at functions on G mod H. And I still get some representations, but they're not all of them, right? So this C of H mod G there is now isomorphic to some direct sum of pi in some sort of set S, where S is probably now not all the irreducible representations, right? It's the irreducible representations that have some magic property with respect to H in some way. And then I get pi to some number, m of pi, and m of pi will be less than or equal to dim pi. And I know that because this just lives in C of G. So instead of looking at all functions on G, I can look at all functions on G that are well behaved with respect to some random subgroup H that I've just come up with, and it's a way of cutting down my representations. Okay? So that was what we did, right? For GL1, we didn't look at random representations of GL1 of the Adels. We looked at random representations which are somehow behaving well under GL1 of Q, right? So now here's the idea then. If G is GLN of K, and so inspired by GL1, G is GLN of the Adels of K, because we're trying to write down some representations of this group that we want to be automorphic representations. G is GLN of the Adels of K. Maybe we want to consider C of H mod G, so functions on, maybe not on GLN of, functions on GLN of K, but maybe there's just some random magic subgroup H, and we want them to be constant on cosets of that. And that's what happened here, right? A Grierson character for GL, a Grierson character for Q was not just a random homomorphism from this thing here to C star. It had to be trivial on Q star. And so really we ended up with representations of this modulo this. So similarly, I want to do this. Because that's going to add some magic extra ingredient, right? Which was just the ingredient we needed, right? When we ignored GL1 of Q, we could do anything. It's gone. We could do anything, and it didn't work at all well, right? And when we put in GL1 of Q, we looked at characters which were actually, constant on Q star, and then all of a sudden, we had some complicated theorem of Weil. So maybe, here's the idea then, maybe an automorphic representation for GLN of the Adels should not be some random representation of GLN of the Adels. So maybe we should focus on functions phi from GLN of K to GLN of the Adels. Okay? So we're going to take all such phi with some properties, right? I don't know, let's not even worry about the properties. They better be differentiable or something. So let's take the set of all nice phi, right? Who knows what nice means? But I want to, there's some infinite stuff here, so I maybe have to say they're differentiable or something. Let's take the set of all nice phi, right? And let's just call it, I don't know, let's just call it kind of curly A0 of GLN of K over GLN of AK. Okay? So what is this A0? This is just functions from this space to the complex numbers, right? Oh, I didn't say that. Focus on phi from G to the complex numbers. There we go. This is a complex vector space. Why is it a complex vector space? Because if I take a nice phi and multiply it by a scalar, it'll still be nice. And if I take two nice phi's and add them up, they'll still be nice. So this is going to be a complex vector space. And it's going to have an action of GLN of the Adels, right? Because just the same as the finite group situation. I quotiented out on the left so I can act on the right, right? I can define an action of GLN of the Adels of K on this, right? It's simply going to be by G star phi of whatever, gamma, is just going to be phi of gamma G, right? And now you just check. Let's just check. Let's just check that G star phi is still a function on the Adels modulo. So I need to check that G star phi of alpha gamma equals G star phi of gamma, right? If alpha is in GLN of K. I just better check that because that's what this means, yeah? If I've got a function on GLN of A mod GLN of K to C, think of that as a subgroup of that, think of that as a space of cosets, and you can imagine phi as a function on the cosets. That's one way of thinking about phi, but another way of thinking about phi is just a function on all of the Adels with the property that phi of alpha G is phi of G, right? For all alpha in GLN of K. Okay? That's another way of thinking about what this function means. What is a function from this weird quotient? This isn't normal in here, you understand this. For GL1 it is, but for GLN, this is some random discrete subgroup living in here. Right? If you want to get some feeling for how GLN of K looks like in GLN of A, then you should think about GLN of Z living in GLN of R. Because formally it looks really similar, right? This modulo some noise coming from some pro-finite bit is just a real Lie group GLN of R. And this is some subgroup that looks a bit complicated, but it turns out when you take the noise into account, that kind of changes the GLN K into GLN of OK. Because if you're locally a unit everywhere, you're globally a unit. So it looks more like GLN of OK, quotiented out by GLN of R. So that's what it looks like. And in fact, this quotient space here is exactly this quotient space here times a sort of a pro-finite amount of noise, which whenever we start looking at representations will all factor through some finite group. Okay? So up to a finite amount of noise, a function on this is the same as a function on this. Right? I mean, at least if K is Q. So, yeah, should we check this? This should be easy. Let me just check this, because I've got a couple of minutes. G star phi of alpha, G star phi of alpha gamma, that equals phi of alpha gamma G. And G star phi of gamma, this is phi of gamma G. And lo and behold, these are the same. So this is good, yeah? Because phi is a function on this quotient space. So phi has the property that phi of alpha x equals phi of x for all x. So in particular, phi of alpha gamma G equals phi of gamma G. So this space here of nice maps phi has the right feeling, right? If G is GL1, then it's kind of good. It looks good because we've somehow quotiented out, right? Maybe. E.g. n equals 1, maybe a Grierson character will be nice. Right? But it's kind of interesting, right? So therefore in A0 of G. Okay? But this is, remember, this is a complex vector space, so maybe a finite sum of Grierson characters. Of completely different Grierson characters. Maybe that will also be nice. Right? Because that's okay. The idea is that this is supposed to be some gigantic, infinite representation of GL1 of the Adels of K, and it's supposed to split up into, infinitely many. This thing here is hugely not irreducible, right? This thing here is going to have lots of factors. This is worth somehow saying, right? So the idea is, I've got this A0 of GLN over K, of GLN of Adels, we've got this space. I haven't defined it properly. It's nice phi's from this thing here. So the idea, just as we did for H, so you see, this is somehow, you should regard this as not the, this is not the group ring of GLN of AK. This is some weird subspace of the group ring consisting of representations of GLN of K that have some magic property, right? That's exactly what's happening here. Take the group ring of some finite group G, you get all representations. If you throw in some random subgroup H, you just get some subset of representations that happen to have survived this kind of coset process, right? So this A0 of GLN of K over GLN of OK, GLN of AK, is not going to be irreducible. It's going to be huge, right? Just like C of H over G was just some random collection of representations. But maybe it'll be a direct sum of pi's, right? With pi irreducible representation of GLN of AK. Right? And maybe those pi's are going to be the automorphic representations. So that's where we're going, you see. With somehow, what I've tried to stress is that we mustn't just look at random representations. We need to look at representations that have a certain magic property that nobody really understands. Okay? And that magic property is behaving very well under GLN of K. So, as an example, we're going to have to think of functions on GL2 of the reals which are well behaved under GL2 of Z. But GL2 of the reals kind of acts on the upper half plane. So it's kind of interesting, isn't it, that there are sort of functions that are on the upper half plane that are kind of invariant under GL2 of Z in some nice way. And so you can kind of see that maybe modular forms will have something to do with this. But anyway, we're getting there. We have to go and get pictured. I don't know where we're going, I don't know what we're doing, but all I know is don't run off without having your picture taken.